Welcome. Today, we're diving into a really cool question in statistics. How do we actually know if something is consistent? We're going to explore what it really means to measure variation and get to know the one tool that's built specifically for that job. Seriously, think about it. You open a bag of chips, you have an expectation, right? You expect that perfect, satisfying crunch. So how on earth does a company make sure every single bag hits that mark? So you don't get one bag that's practically dust and another that could break a tooth? Well, that perfect crunch is no accident. It's all about controlling variability. In the stats world, we call this the variance, or the standard deviation. And to make sure that variation doesn't get out of hand, you need a very specific tool to check on it. And that tool, my friends, is the chi-square test. I know, it sounds kind of intense, but it's really our hero for today. It's designed for one specific job, answering questions about consistency. So, what does that actually mean? Basically, this test lets us grab a sample, like a handful of those chips, and see if its consistency, the spread of its crunchiness, lines up with what the company claims it should be. We're checking if the reality in our hands matches the promise on the bag. Okay, let's look at the formula. Don't let the symbols freak you out. It's simpler than it looks. That first part, the chi-squared, that's our chi-square value. And we get it by taking n-1, which is just our sample size minus 1. We call that degrees of freedom. Then we multiply that by s squared, which is the variance we found in our sample. And finally, we divide the whole thing by sigma naught squared, which is the official claimed variance we're testing against. That's it. All right, I need you to lean in for this next bit. Seriously. Because what I'm about to say is the single most important, can't forget it, absolute deal breaker for this entire test. You can think of the chi-square test kind of like a super sensitive, high-tech scientific instrument. It gives you incredibly precise results, but only if you use it in the perfect, sterile, lab-controlled conditions. If those conditions aren't met, your results are basically garbage. And this is the condition. I'm putting the direct quote right here because it is that important. When we say a test is not robust, it means it's fragile. It breaks easily. And what breaks it is departures from normality. In plain English, if your data doesn't look like a nice, classic, bell-shaped curve, this test will lie to you. So here's what you need. 2 things. First, your data has to come from a random sample. That's pretty standard for most tests. But second, and this is the big one, the non-negotiable one, the population that your sample came from must be normally distributed. There are no ifs, ands, or buts about it. All right, enough with the scary warnings. Let's get our hands dirty and actually see how this thing works with a real example. So let's pretend we're the quality control manager at that chip factory. We grab a random sample of 25 bags, and we find that their standard deviation is 2.4. Now, the company handbook claims the standard deviation should be exactly 2. We want to know if our sample is weird enough to challenge that claim, and we'll use a 5% significance level, our alpha, as our cutoff for weird. So let's plug and chug. First, we need variance, not standard deviation, so we square our sample standard deviation. 2.4 squared is 5.76. Next, we square the company's claim. 2 squared is 4. Perfect. Now we just pop it all into the formula. That's 24 degrees of freedom times our sample variance of 5.76, all divided by the claimed variance of 4. And we get a chi-square test statistic of 34.56. Okay, great, we have a number. But so what? What does 34.56 actually tell us? Is that a big number, a small number? Does it mean we should be worried? This is where we figure it out. We compare our number to what we call the rejection region. These are the critical values we get from a chi-square table. For our specific test, the alarm bells would go off if our number was smaller than 12.41 or bigger than 39.35. But look at our result, 34.56. It falls right in between those two. It's in the safe zone. So, what's the final verdict? Well, in the formal language of statistics, we say we failed to reject the null hypothesis. All that really means in plain English is that, based on our sample, we just don't have enough evidence to call the company liars. For all we know, the true standard deviation really could be 2. Okay, before we wrap this all up, I want to give you a quick sanity check. A little checklist of the most common mistakes people make with this test so you can avoid the headaches. First, and you knew I was going to say this again, you absolutely must double-check that your data is normal. The test is just way too sensitive. Second, a classic rookie mistake. People plug the standard deviations straight into the formula. Don't do it. You gotta square them to get the variance first. And last, just remember the chi-square distribution isn't that nice symmetric bell curve. It's skewed off to the right. So, here's the bottom line. The chi-square test is a fantastic, super specific tool. It is your absolute go-to when you need to test a claim about a population's consistency. But like any specialized tool, it only works if you play by its rules, especially that huge, all-important rule about normality. And I'll leave you with one final question to chew on. We've talked a lot about the dangers of having too much variation, but when might having too little variation be just as big of a problem? In what kinds of systems is a bit of randomness not just good, but actually necessary to be healthy? Think about it.